Good evening, ladies and gentlemen. Thank you very, very much for being here this evening. My name is Jean Hoerni, and I'm the CEO of the museum, and it's my pleasure to welcome you to the second of two very special nights this week, marking the 50th anniversary of the most important moment since man emerged as a life form. That's how Isaac Asimov described it, and that's good enough for us. And now for tonight's program. This week we've heard quoted scientists, technologists, historians, philosophers, even a theologian at one point, I think. But I'm going to invoke one line of work that nobody has yet mentioned this week, and that's a hockey player. Wayne Gretzky described the history of his great career in terms of two simple rules. The first rule was, I found early on that I missed 100% of the shots I didn't take. And the second was this, I don't skate to the point where the puck has been, I skate to the point where the puck is going to be. If semiconductor science were a hockey game, you might say that in 1965, Gordon Moore predicted for the world the point where the puck was going to be. And sure enough, it seems always to have been there. And for 45 years, the scientists and engineers of computing have been skating to that point, a rapidly moving point along an ascending curve whose end has long been predicted, but has not yet been reached. So it turns out that Moore's law has proven to be a kind of covenant between time and technology, remarkable, elegant, and enduring. But tonight, if I can stretch that hockey analogy just a little bit further, all the way to the breaking point probably, we are going to return all the way back to the opening face-off, the invention of the planar process for fabricating a semiconductor, the stories of how it happened, and the people responsible for that game-changing breakthrough. As I said the other night, the wonderful feature of working in computer history here at the museum, of course, is that many of those who made the history are available to tell it as well, and they do a beautiful job of it. We're taking full advantage of that tonight, and in doing so, as I said, we have an extraordinary partner in the Chemical Heritage Foundation, and we were fortunate enough to have the Foundation's Chancellor, Arnold Thackeray, with us on Wednesday night. And tonight, I am pleased to welcome, to open the proceedings, the distinguished past president of Haverford College and now president of the Foundation, Tom Tritton, who will get us started. Tom, welcome.
Thank you, John. Thank you for hosting such a most excellent week on the history and impacts of the semiconductor industry. On the very off chance that you don't all know what the Chemical Heritage Foundation is, I will tell you that we are a library, a museum, and a center for scholars headquartered in Philadelphia with tentacles all around the world that is dedicated to preserving the history and telling of the story of the chemical and molecular sciences. Should you come to our museum, I will give you the private president's tour, so please do so. The Computer History Museum and the Chemical Heritage Foundation have several things in common. In some sense, we're fraternal twins. Both organizations preserve and teach the history of a science. Both are celebrating the accomplishments that the integrated circuit made possible, accomplishments we remember here tonight and all week on the 50th anniversary. And both organizations are headed by devilishly handsome, bespectacled men who love hockey analogies. The only person who actually agrees with that is John. But one of the fields of current scholarly interest at the Chemical Heritage Foundation is to preserve the chemical history of electronics. Yes, I meant that exactly the way I said it, the chemical history of electronics. The production of semiconductor electronics relies fundamentally on chemistry and the chemical synthesis of materials. And the rise of the integrated circuit is one of the biggest stories in the history of chemistry, as well as one of the biggest stories in the history of computers in the second half of the 20th century. For these very obvious reasons and more, CHF is pleased to be able to join the Computer History Museum and the Institute of Electronics and Electrical Engineers in raising a glass as the integrated circuit turns 50. I won't actually be the one that raises the glass, because our master of ceremonies tonight is David Brock. So I will turn the job over to David, and I would also like to invite today's speakers to the stage as well. Christophe Lecuyer, Leslie Berlin, Gordon Moore, and Jay Last. David Brock, it's yours.
After you, Leslie. Thanks, Tom. After you. Well, thank you very much, Tom, and thanks so very much to everyone for attending and participating in these events. I'm, as you heard, David Brock. I'm an historian of science and technology and senior research fellow with the Center for Contemporary History and Policy at the Chemical Heritage Foundation. It's my sincere honor to have been part of the team that organized these anniversary events and to moderate tonight's program. Let me begin with just a few words about the choice of 2009 as a year to mark the 50th anniversary of the integrated circuit. As my colleague David Laws said in his remarks on Wednesday evening, there are many arguments for dates that range from even the early 50s to the middle 1960s as marking the true emergence of integrated circuitry. Among these contending dates, 1959 has the particular virtue of inclusiveness. The events of 1959 highlight that the development of the integrated circuit was as much the achievement of a broad technical community as it was the result of remarkable individual achievements. The late 1950s and early 1960s was an extraordinary period in the development of semiconductor electronics. Military interest in and the semiconductor industry's pursuit of diverse approaches to microcircuitry took off in the second half of the 50s. 1959 saw a burst of intellectual activity across the industry as Kurt Lehovic of Sprague, Jack Kilby of Texas Instruments, along with Jean Hoerni and Robert Noyce of Fairchild Semiconductor, and others, all filed patent applications that held the conceptual keys to the development of the modern integrated circuit. Jay Last's team at Fairchild, which would create the first planar integrated circuits, also began their efforts in 1959. The program held here on Wednesday evening highlighted the intense activity within the semiconductor community during the late 50s in the direction of microcircuitry and miniaturization. Here was a great diversity of approaches, ranging from new materials to functional devices, and from hybrid circuits to novel packaging schemes. One developmental line within this diversity was semiconductor integrated circuits, the line pursued at Texas Instruments with its solid circuit approach, and also the line that was pursued at Fairchild Semiconductor, resulting in the planar integrated circuit. The planar integrated circuit, developed at Fairchild Semiconductor in the early 1960s, became the electronics technology through which we have created our contemporary digital world. Through decades of dedicated, innovative, and indeed costly efforts, the semiconductor community has made silicon planar integrated circuits indispensable to modern life and largely synonymous with electronics itself. Two of the key figures associated with the development of the planar integrated circuit at Fairchild Semiconductor are unfortunately no longer with us, Jean Hoerni and Robert Noyce. Fortunately, tonight we will hear from two of the leading historical experts on these individuals who will open our program this evening. Christophe Lecuyer will give us a view of Jean Hoerni and his development of the planar process for manufacturing electronic devices in silicon. Leslie Berlin will present a picture of Robert Noyce and his conception of the planar integrated circuit. We'll then hear from two of the co-founders of Fairchild Semiconductor, Gordon Moore and Jay Last. Gordon Moore will discuss the background to the planar integrated circuit efforts at Fairchild, and Jay Last will recount his experiences as the leader of the team that moved from conception to realization, creating the first planar ICs. For whatever time remains following the talks, we'll have a question and answer session for which you can submit questions using the cards provided. They'll be collected toward the end of the talks. And we'd like to make a special recognition that in the audience tonight are a number of individuals who played important roles in the early history of Fairchild Semiconductor and the firm's efforts in semiconductor manufacturing and integrated circuits in this period. Julius Blank, Tom Saw, Bob Norman, Harry Sello, Lionel Katner, Don Farina, Murray Siegel, Aaron Saxena, Dick Anderson, and others. My sincere apologies to any of you whom I've missed. On behalf of the organizers of this event, congratulations to you for your breakthrough achievements. It's now my pleasure to introduce to you Christophe Lecuyer, an historian of science and technology who earned his doctorate at Stanford, currently the principal economic analyst in the Office of the President of the University of California, and the author of Making Silicon Valley, Innovation and the Growth of High Tech, 1930 to 1970. Christophe.
So Jean Hoerni is not well known, but he played a key role in the development of IC technology and the growth of Silicon Valley. Hoerni, as you know, was a Swiss. He was born and raised in Geneva. He obtained a bachelor's degree in mathematics from the University of Geneva before moving on to a PhD in physics at Geneva as well. And interestingly, he later got a second doctorate also in physics at Cambridge in England. In 1952, he moved to California, where he conducted research on electron diffraction at Caltech under the direction of Linus Pauling. Several years later, Hoerni accepted a research position at Shockley Semiconductor Laboratory. Shockley, as you know, had been recently established by William Shockley, the co-inventor of the transistor, the Bell Labs. Shockley Semiconductor was really the first silicon startup in Silicon Valley. And at Shockley, Hoerni worked on the calculation of diffusion curves for the making of silicon devices. He also fabricated PNPN diodes, the functional device that Shockley had invented a few years earlier at the Bell Labs. And this was indeed a very difficult assignment. These things were really difficult to make. And this assignment really turned Hoerni into a semiconductor engineer and also an experimental physicist. He had been trained before in theoretical physics, really. So when it became increasingly difficult to work with Shockley, Hoerni and his fellow co-workers, namely Chelas, Gordon Moore, Robert Noyce, Victor Greenwich, Sheldon Roberts, Julie Blank, and Eugene Kleiner rebelled against Shockley. And with financing from Fairchild Camera and Instrument, they started Fairchild Semiconductor in the fall of 1957. So what kind of person was Jean Hoerni when he started Fairchild Semiconductor? So his coworkers describe him as very Gallic, charming, temperamental, and also intensely competitive. And they also recall that Hoerni was most innovative when he was angry and felt unappreciated, and I understand it was often the case. So these character traits really served him well at Fairchild, and in some ways led to, and partially to the invention of the planar process. I'm sorry. So the planar was really a fundamental innovation, one of the main innovations in the history of semiconductor technology and industry. In effect, the planar process was really the starting point for 50 years of semiconductor manufacturing technology. So the planar really provided a new way of making silicon transistors. Up until Hoerni's invention, the main device structure for silicon transistors was the Mesa transistor, which you see here. The Mesa transistor, developed at the Bell Labs in 1955, looked like a southwestern mesa, hence its name. The emitter and base regions of the transistor overlooked a much larger collector region. And under this scheme, the p-n junction of the transistors were really exposed to the outside. So that's a key aspect of the Mesa transistor. In contrast, the planar transistor invented by Jean Hoerni was characterized by its flat surface. A layer of silicon oxide covered the emitter, base, and collector regions of the transistor. And most importantly, this layer also protected the junctions of the transistor. So that's really one of the main aspects of that planar technology. So in tandem with the invention of the planar structure, Hoerni conceived a process to fabricate it. The first step in the planar process was the growth of a layer of silicon oxide on top of the silicon wafer. And then Hoerni used that layer of silicon oxide to diffuse the emitter and the base regions of the transistor. In a very innovative move, Hoerni decided to leave the layer of the silicon oxide after processing. And the practice until that time was to take it off, okay? And it was widely believed, especially at the Bell Labs, that this oxide layer was dirty and had to be removed after processing. So one of the key insights that he has is to keep that layer of silicon oxide on top of the regions, the emitter, base, and collector regions. So how did the invention of the planar come about? It really came about in two different phases. In December 1957, a few months after the formation of Fairchild Semiconductor, Hoerni wrote an entry in his patent notebook on a method of protecting p-n junctions at the surface of silicon transistors by oxide masking techniques. So this entry, of which you see here the first page, I understand the document is also, the real document is on the other side there. This entry really summarized Hoerni's planar ideas. And these ideas, however, remained largely dormant for much of 1958, as Hoerni focused on a different project, namely the fabrication of a PNP mesa transistor, which later became Fairchild's second product. It was only in late 1958 or very early 1959 that Hoerni and the technician came back to the idea of the planar process, the planar structure, and made a half planar structure, namely a transistor structure where the junctions between the emitter and base regions was covered by a layer of silicon oxide. And Hoerni and his technician found that this half-planar structure offered better electrical characteristics, especially in terms of amplification. So these interesting results, encouraged Hoerni to fabricate a full planar transistor, and especially to planarize the NPN mesa transistor that Fairchild Semiconductor had recently introduced to the market. So this transistor had a major reliability problem. The mere fact of tapping the metal can that protected the transistor with a pencil led to transistor failure. So this was a major reliability problem, and especially for a startup that was serving military markets. And as you know, the military markets then and now are very much put enormous emphasis on reliability. So in many ways, the survival of Fairchild was at stake, and that was in 1958, 1959. So these mesa transistors failed because their exposed junctions attracted specks of dust that then shorted the transistors. And Hoerni thought that the planar structure, where the junctions were actually protected by an oxide layer, would solve this reliability problem. In March 1959, Hoerni made the first planar silicon transistor, which you see here. This device had remarkable characteristics. It was extremely reliable. It was especially immune to the reliability problem of the mesa transistors. And the planar transistor also had much better electrical characteristics, especially in terms of amplification and switching. But as Hoerni discovered, the planar transistor was very difficult to make indeed. It took about a year for Hoerni and the group led by Harry Sello to transform this planar technique into a manufacturing process and a stable manufacturing process. And this robust process enabled Fairchild Semiconductor to planarize its line of mesa transistor and also to bring to the market planar diodes as well. So what was the impact of Hoerni's planar innovation from 57 to 59? Arguably, the planar process saved Fairchild Semiconductor and certainly transformed it into a major manufacturer of silicon devices for the military market, but also for the commercial sector as well. Fairchild's planar expertise also put the company at the forefront of semiconductor technology, a position that the company retained for much of the 1960s. And in contrast, the Bell Labs, which until then had been the leading organization in semiconductors, was really relegated to a more secondary position. Maybe more importantly, Hoerni Planar's invention made the planar integrated circuit possible. The planar IC, as you know, was invented by Robert Noyce immediately after Hoerni revisited his planar idea in early 1959. And this planar integrated circuit was later put into silicon by Jay Last and his group at Fairchild, and especially I think of Izzy Haas and Lionel Kartner. Not surprisingly, the planar process was widely adopted in the semiconductor industry. By the early 1950s, all firms making silicon devices converted to planar technology, and those that didn't failed, essentially. So that was really a key breakthrough and a key change in the history of semiconductor technology. And interestingly, the planar patents that Hoerni filed on his ideas generated one of the largest royalty streams in the history of the semiconductor industry. And they generated about $100 million in the late 60s and early 1970s. And these monies were especially important to Fairchild in the late 60s and early 70s and kept the company afloat financially, essentially, at that time. Maybe more importantly, the planar process established silicon as the main material for semiconductor electronics. And it enabled Fairchild and other firms oriented towards silicon to displace germanium as the dominant material for the making of semiconductor devices. So the planar process was a major innovation indeed, but it was not Hoerni's only contribution to semiconductor technology and industry. In the late 1960s, 50s, and 1960s, Hoerni made important process and product innovations. At Fairchild, Hoerni invented gold doping, a critical technique that speeded up the switching, the transistors, essentially. He later developed a very innovative line of field effect transistors at Amelco. And in the late 1960s, he engineered the first CMOS watch circuits in Silicon Valley. In addition, Hoerni started a series of semiconductor companies in the region. In 1961, with Jay Last, he started Amelco Semiconductor, a division of Teledyne. A few years later, he created Human Carbide Electronics, a division of Union Carbide. In 1967, he formed Intersil, a company that focused on the making of watch and memory circuits. And Eurosil, another Hoerni startup, followed in 1972. And Eurosil was really Intersil's European subsidiary. It was based in Munich and made circuits for the watch and clock industry in Germany. And Hoerni later moved back to Silicon Valley, where he established Telmos in 1981. So a series of companies from the 50s to the 1980s. Toward the end of his life, Hoerni founded and financed the Central Asia Institute, an organization that builds schools, especially schools for girls, in northern Pakistan. And to date, the Central Asia Institute has built 78 schools and provided education to more than 28,000 children in northern Pakistan and in Afghanistan. So Hoerni had a very unusual life trajectory from boyhood and adulthood in Switzerland, early in young adulthood in Switzerland, to inspired engineering in Silicon Valley, and then to the building of a network of schools in Pakistan and Afghanistan. Across his life, Hoerni made very important technological and social innovations. Of course, invented the planar process, this key technology that is at the very core of ICs. But Hoerni also innovated socially. He co-founded Fairchild Semiconductor that really became the model for subsequent semiconductor firms in Silicon Valley. But he also, I think, and importantly, helped set patterns of entrepreneurship in Silicon Valley. He was one of the Valley's first foreign entrepreneurs and also one of the Valley's first serial entrepreneurs. And his innovations also went into the building of schools in a very remote region in Central Asia. Thank you.
Well, thank you very much, Christophe. It's now my pleasure to introduce to you Leslie Berlin. Leslie is project historian for the Silicon Valley Archives at Stanford University and also writes the prototype column on innovation for the New York Times. She's the author of The Man Behind the Microchip, Robert Noyce and the Invention of Silicon Valley. Leslie.
Well, I'm very honored to be here with such distinguished panelists to tell you about Robert Noyce and his contributions to the integrated circuit. So in the next 15 minutes, I'm going to do three things. First, I'm going to introduce you to Noyce. Second, I'll talk to you about his technical contributions to the integrated circuit. And then finally, I want to talk to you a little bit about his contributions of a different sort, which were his decisions in about 1964 to price the integrated circuit very aggressively so that they could break into the commercial markets. I have exactly one slide, which I'll show you now. Who was Robert Noyce? So this is a portrait of the founders of Fairchild Semiconductor shortly after they launched the company in September of 1957. So Noyce is front and center with his arm over the back of the chair, and I would like to go around the group. So moving clockwise from Noyce, we have Jean Hoerni. Next to him, we have Julius Blank, who is here in the audience today. Next to Julius is Vic Greenwich, and next to him, directly across the table from Noyce, is Eugene Kleiner. Following on that is Gordon Moore, and then, pardon me, leaning back in his chair is Sheldon Roberts, and finally, we have Jay Last with his arm on the table. And there's a reason that I wanted to show you Noyce in the context of this larger group, and I think this is going to be a theme for the evening. Every success that Noyce achieved came as part of a group. Fairchild Semiconductor, Intel, the integrated circuit, starting the Semiconductor Industry Association, Semitech. Noyce did none of these things alone. Very, very often, his best ideas were inspired by the people around him. And Noyce also was a bit of a perpetual motion machine intellectually. He had ideas sort of falling off of him left and right. As Gordon said, Bob was a man of many ideas, some of them good. And he always needed people around him to help separate the wheat from the chaff. So that was me, not Gordon saying that about wheat and chaff. So who was the Robert Noyce that you see in this picture? Here he's about 30 years old, making him one of the old men of this group. He had grown up in Grinnell, Iowa, where his father was a Congregationalist minister. In 1949, he graduated from Grinnell College with double major in math and physics. At Grinnell, he was quite the man about campus, lots of girlfriends, a champion diver, a madrigal singer. He was a Phi Beta Kappa. He always said that the award that he won at Grinnell that mattered most to him was the Brown Derby Award, which was given to the senior man who achieved the best grades with the least amount of work. So in 1953, he received a PhD in physics from MIT, where he did his doctoral work on the surface states of quartz and magnesium under the experimental physicist Wayne Nottingham. And after leaving MIT, he worked on germanium transistors at Philco in Philadelphia. And then in 1956, he accepted a job with William Shockley, which is where he met the other fellows in this picture, and they went on to start Fairchild Semiconductor. So, what were Noyce's technical contributions to the integrated circuit? His thinking in this direction was really kick-started by Jean Hoerni, and specifically Hoerni's January 1959 notes about the planar process. When you look at Noyce's notebook on his first musings on the integrated circuit, which are also from January 1959, he refers specifically to the use of a silicon oxide layer as an insulator to isolate contact strips from the underlying silicon. And this is also a quote, protection of the junction at the surface with an oxide layer. So you see that the debt to Hoerni is quite significant. In this same entry, Noyce also suggested that PN junctions could be used to isolate components from one another. And his thinking in this area is nearly simultaneous with that of Kurt Lehovic at Sprague, who holds the patent on this technique. And finally, Noyce suggested a means of interconnecting the components via metal paths laid down over the oxide layer. So here you have Noyce pulling together three ideas, the planar process and these ideas about junction isolation and metal interconnections, to build a monolithic circuit, something the industry had been pursuing for years, and the feasibility of which had been demonstrated a few months earlier by Jack Kilby at Texas Instruments. When I see this, I see it as an elegant act not only of innovation, but appropriately enough of integration of other ideas already in play. Noyce himself talked about drawing from a bag of tricks to combine elements to make the integrated circuit. And some of these tricks were his own, and some of them came from other people. Again, Noyce was one in a group of innovators. With Jack Kilby, he is considered to be the co-inventor of the integrated circuit. But when I look at Noyce's work in the context of all the work that was happening at Fairchild at that time, the analogy that always springs to mind for me is that of a pitcher who has pitched a perfect game. When you think about a perfect game, you've usually got the first baseman killing himself to get to the bag before the runner. You have a catcher who's down there sort of choosing the perfect pitches that are going to be calibrated to each batter's weakness. You have these outfielders making these amazing catches. And the record books say that the pitcher pitched a perfect game. And really, it was a group effort. And certainly, that was the case with the integrated circuit at Fairchild. Just one other thing that I want to be sure to mention on the technical side. Noyce's patent said it should be possible to build an integrated circuit using these techniques. And that was an essential insight. It was not the final insight needed to build a functional integrated circuit. The gap between should be possible and the reality of a functional device is huge. And I think Jay last will be talking about the innovative work that was required to bridge that gap. So 2 months after Noyce wrote down his ideas about the integrated circuit, he left the lab for a management job, essentially never to return. The general manager of Fairchild Semiconductor had departed to start his own operation, and Noyce took over his job. This was not something Noyce wanted to do. I mean, this is a guy who a few months before had called management, and I quote, a chore that takes time away from useful work. But he agreed to a 6-month trial run, and he said he did even that with a great deal of fear of inadequacy. Julie was saying to me before this started that Julie remembered saying to Bob Noyce, God, I hope we're not losing a great researcher for a mediocre manager. And Noyce said, yeah, it might really be the case here. And it was as general manager that Noyce made his second set of contributions to the integrated circuit. Fairchild introduced its first commercial IC, a flip-flop, in early 1961. And as Christophe was mentioning, or perhaps it was David, was alluding to, up to that point, 100% of integrated circuits went to military uses, and you guys know why. These things were incredibly expensive compared to discrete components. A simple gate made with an IC would be $150, and you could build the exact same thing with discretes for $3. And so this meant only customers with extreme constraints on size and weight, but essentially limitless cash could be a customer. And that, of course, meant the US military. So the commercial introduction of the integrated circuit was met with great interest. It was covered all over the place, but not really great sales. And as late as 1963, you were still hearing that integrated circuits were going to basically remain on the R&D level until there was some sort of technical or design breakthrough. Noyce really saw things differently. He once said, "The selling of new ideas is an engineering problem." And he thought that the IC didn't need a technical overhaul, or a design overhaul. It just needed to be cheaper. And so in the spring of 1964, he decided that Fairchild would sell its low-end flip-flop ICs for less than it would cost a customer to buy the individual components and connect them himself, and less than it was costing Fairchild to build the device. This was a pretty radical move. Prices had already begun to fall somewhat, but by about 40% at that point, but nothing like this. It absolutely shocked the competition, and Gordon, you told me you were actually pretty surprised by this yourself. In effect, Noyce was betting that experience curves and economies of scale would enable the company eventually to build the circuits in such quantities and for so little that it would be possible to make a profit even on this seemingly ridiculously low price. And it worked. In less than a year, the market had so expanded that Fairchild received a single order that was equivalent to 20% of the entire industry's output for the previous year. I would argue that Noyce's decision to cut the price of the IC to stimulate demand was as important a part of the device's invention as his technical work. With this move, Noyce helped to transform the IC from a specialized piece of military hardware to the heart of the commercial and later consumer electronics revolutions. So let me just quickly cover what happened with Noyce after the integrated circuit. Fairchild, under his stewardship, grew incredibly fast, sort of the Google of its day, and then it crashed. Noyce is at least somewhat responsible for both the rise and the implosion. In 1968, he and Gordon Moore left to start Intel. And 9 years later, Noyce and 4 other semiconductor executives started the Semiconductor Industry Association. And from 1988 until his death in June of 1990, he was only 62, Noyce was the founding CEO of Semitech, the government industry manufacturing consortium. Through it all, Noyce devoted a good deal of energy to mentoring young entrepreneurs, an activity that he called restocking the stream I fished from. Foremost among these entrepreneurs was Steve Jobs, for whom he had a deep affection that Jobs certainly returned. There were many more of these entrepreneurs. Noyce was no sentimentalist, and certainly not someone to ruminate over his past, but I think that throughout his life, he remembered the early years of Fairchild with great, great fondness. The valley was young, the country was booming, and Noyce himself, he was so young and he was so bursting with new ideas. He would wake up in the middle of the night and tiptoe downstairs to write things down on the kitchen counter in a little notebook he kept there. He likened those early years at Fairchild to riding a fast horse. He said it was scary at times, but it was always exhilarating. It was, he said, a time when it seemed anything was possible. Thank you.
Thank you very much, Leslie. Our next speaker is Gordon Moore. Gordon earned his PhD in physical chemistry and physics from Caltech and was a member of the staff of Shockley Semiconductor before co-founding Fairchild Semiconductor and then later the Intel Corporation. In addition to providing business and technological leadership for these two firms, he made several key contributions to silicon semiconductor manufacturing technology. When the planar integrated circuit was developed at Fairchild, Dr. Moore was the director of R&D. Gordon.
Okay, thank you. I'm going to plow some of the same ground that the first two speakers did, but maybe with a slightly different spin. My role, presumably, was to kind of lay out the background for the integrated circuit at Fairchild, and Jay Last will pick it up from there with how it was actually accomplished. It's probably a very Fairchild-biased approach to the IC, but what else could you expect? The early days of Fairchild, the 8 of us left Shockley Semiconductor Laboratory after about a year and a half of essentially learning on the job. Noyce was the only one of us that really had any semiconductor experience before joining Shockley, so the rest of us learned a bit about the technology, where we thought it ought to go, and one thing and another, in some rather rudimentary facilities with rudimentary equipment. Management problems at Shockley motivated us to look for something else. We were all going to run off and look for jobs when one of the group, Gene Kleiner, wrote to a friend of his father's, actually his father's stockbroker, said a bunch of us like working together, you think that the company like to hire the whole group. And they sent out a senior partner and a young Harvard MBA to talk with us. The young Harvard MBA was named Arthur Rock. Some of you may have heard of him. And they met with us, and after an evening discussing various things, they said, you don't want to find new jobs, you ought to set up your own company, and we will find you support. Yeah, okay, that way we don't have to sell our houses and move. So that was the motivation that got us to set up Fairchild. Now they had to find money. And the idea at that time, before the existence of really venture capital, was some corporation might like to have a semiconductor division, and we would be happy to set that up for them. So we sat down with a copy of the Wall Street Journal and looked at every company we could think of that might want a semiconductor division. I think there were 35 of them in total. Arthur and Bud Coyle, the senior partner, visited all 35, and they all turned it down without even talking to the group. Fortunately, they met up with Sherman Fairchild kind of accidentally. Sherman loved technology, introduced them to the chairman of Fairchild Cameron Instrument, and they were willing to commit $1.3 million for the possibility of setting up a semiconductor company. That, excuse me, was the beginning. Now, we set out with the objective that Shockley had abandoned of trying to make a double diffuse silicon transistor. Shockley moved on to a 4-layer diode, which was a much less useful device, and we were unable to convince him to stick with the transistor. We had to rent a building. Some of you were there today as we dedicated a plaque to the original Fairchild building on Charleston Road. Excuse me, this darn cough won't go away. The building was 14,000 square feet, which seemed like a huge amount to us at the time. And we knew we had to do some certain things in order to get the company going. The first thing we realized was we had to hire someone to be our boss. We learned at Shockley that management wasn't something that people necessarily came by naturally. And so one of our objectives was to hire someone who would be the general manager while we filled in the technical positions. We put an ad in the Wall Street Journal. We discovered that every salesman thinks he's general manager material. But we finally did find a person with some experience in management and also in semiconductors, Ed Baldwin from Hughes Semiconductor, making diodes at the time. And Ed came and taught us some things that were very useful in getting the company going. The rest of the original group kind of split up responsibility for setting up the technology. Those days you had to build your own equipment. Nothing suitable was available commercially. So we each took a particular part of it and started working on it. But Jean Hoerni was a theoretician. He wasn't, at that time, very adept at setting up equipment, so he was off calculating diffusion curves and one thing and another, things we would need as we moved ahead. But he recognized something that I guess we all inherently knew. If I can figure out what button to push. That was the wrong one. Help. I got this thing because it has a laser pointer in it, but whoops, other way. Okay, here I am. These are some very simple ideas just to get the idea across. If you make a mask diffusion, this is oxide out here diffusing an area in the center. Jean recognized that in a material like silicon, the diffusion goes as far sideways as it does down here. The diffusion is isotropic, which means that the actual place the junction existed was underneath the original oxide, the dotted line in the top view. Now, it's not very far under. You know, with the things we were working with at that time, it's about a 10,000th of an inch. But nevertheless, far compared with the active part of the junction. And he suggested, well, why don't we leave the oxide on there to protect it? Because we all knew that where the junctions came to the surface was a very sensitive part of these devices. It's an area of high electric field that attracts everything that happens to be loose around the area. And he thought that leaving it on might be advantageous. How do we get to the next slide? I better be...
Just hit the space.
Push enter?
Yeah.
And this was the idea of the planar transistor. The Mesa transistor, we chopped off, made this high electric field junction at the side, and had to suffer the consequences. And we made good transistors. But the idea of the planar transistor with all of these junctions would be left under the oxide and therefore hopefully protected. But we were too busy to try it. You know, we were wanting to get our first products out. That was clearly job one. How could we get on the market, have something that we could really sell? And besides that, in order to leave the oxide on and make the structure, required 4 mask layers instead of 3. Bob Noyce and Jay Last had carefully set us up a technology that made 3 masks fine, but we hadn't planned on a 4th one, so we really weren't prepared to do it. So it kind of languished as an invention in Jean's notebook for quite a while. Jean made other contributions. One that he also derived from his theoretical calculations was that gold wasn't so bad after all. Gold was considered the nemesis of the semiconductor industry at that time. It killed the lifetime of carriers in silicon very dramatically. And for some reason, we thought we needed significant lifetime to make these transistors. Jean calculated he didn't really need that much anyhow, and you could improve the switching speed by having the carriers return more rapidly to equilibrium if you had gold in there. So he put gold on the back of the things, and not only did it improve the switching speed, it performed an operation we called gettering, which cleaned up the junctions of other things that used to mess them up and made nice, hard junctions. Really a serendipitous effect that was important in some of the early switching transistors to get the speed that we really needed for the computers. Well, while Jean may not have been useful in setting up the equipment, he quickly developed an ability to use it. In fact, he became a tiger in the diffusion area. He would walk through with one of his experiments looking for a furnace with nothing in it and use that to do whatever operation he wanted to do, adjusting his time to the temperature that was actually there. Can you imagine him wanting to put some of his gold-doped devices in the furnaces that were being used for NPN production transistors at the time? But Jean did things in a hurry. Now, collectively, I don't remember exactly who did it, we figured out a way to leave the oxide on the emitter base junction, that's this junction here, in a MESA transistor by doing a differential dipping. And therefore, we could try leaving the oxide over a junction. We couldn't do it on the one on the side here, but we discovered that by leaving the oxide on this, the current gain of the transistors was increased and much more stable than it was otherwise. So we got excited about leaving the oxide on based on that experiment. It was one of these quick and dirty deals, though. And then we went on to make a full planar transistor after we got our first NPN and PNP MESA transistors into production. The story, which Harry Sello confirmed this afternoon, is that Jean demonstrated this first planar transistor by spitting on it and showed that the characteristics were preserved. Now that sounds a little aggressive to me, but it sure fits Jean's personality perfectly. I have to show a picture of the first planar transistor, partially for its historical value, for me because it's one of the few products I ever designed the geometry of that went into production. This 30 mil diameter device was the same size as our original MESA transistor. It was an important product in getting Fairchild established. Now, after we saw the results of the planar transistor, Noyce was working with John Rawls, a patent attorney in Palo Alto, to develop the patent application for the planar transistor. It wasn't unusual for somebody other than the inventor to work with a patent attorney. That's a different kind of a job, let's say. And John Rawls asked Bob, he says, this sounds important. Are you sure you're looking at all the ramifications of it? And my view of the world is that stimulated Noyce's thinking to find out what else he could do and led to the ideas of the integrated circuit. Now, an integrated circuit needs several components. You've got to do transistors and diodes. These are what semiconductors do, so that's okay. You need resistors. Resistors are no problem. We characterized our diffuse layers by what their sheet resistance was, how many ohms for a square structure. And you just make a long, skinny one if you want a high resistor, a short, fat one for a low resistor. So resistors were okay. Small capacitors were made by the junctions, which have a capacitance associated with them. And these were the things that Jack Kilby demonstrated you could make out of silicon also. You could make all the components. You needed two more things. You needed isolation, because all the devices of a transistor like this are made with a third terminal common. Now, those of you less than 50 years old probably never thought you'd worry about isolation because MOS transistors don't require it. They're self-isolating. But this was the bipolar days, and isolation was one of the major things you had to have. And the second thing, of course, is interconnection. How do you connect the resistor to the transistor and so forth? Noyce came up with inventions on both of these. For isolation, he suggested you put extra junctions in there so that one junction was always biased in the non-conducting direction, so there wouldn't be any current flowing from one region to another. Unfortunately, he didn't get a broad patent on that invention. He got a couple of rather detailed versions of it because Kurt Lehovic had anticipated the same kind of a structure a couple of months earlier and filed a little bit ahead of Bob. So that invention actually got abandoned. But the interconnection, running the metal up over the oxide, was the patent that issued and was something that was argued with Texas Instruments for quite a while before we finally settled how that went. If we look at a cross-section of an integrated circuit, I just am doing this fairly schematically. The transistor was fairly obvious. We had, whoops, what the hell am I? That was a fat finger problem. Beyond the beyond the laser, I also poked the thing. Anyhow, an NPN transistor, which would ordinarily be the substrate, is now pulled up to the top surface to make a contact. And then you can see a metal connection going over the oxide. Again, the back bias junctions, one of these is always back biased, so the N region here is not connected to that one. To a diffuse region that could be the same as the base here to make a resistor. This was the kind of things that we had to happen, and you've seen photos of the ICs that show the structure. You can see resistors here. This is a terrible picture. I always wish we had a nice clean one that would say, but this is the surviving picture of the first integrated circuits. You can see the isolation structure buried down in here. These were the important things to make the integrated circuit work. Now, about this time, Ed Baldwin, the general manager we had hired, bailed out to set up his own company, Ream Semiconductor. We had a debate, should we go and hire another general manager? And after a significant discussion, we decided to see if we get Noyce to pursue the job. So Noyce took over as general manager. I replaced him as director of R&D, and Jay Last took on the project of developing the first integrated circuits. Jay will tell you a lot more about that. Bob Norman, who's in the group tonight, handled the circuit design for the integrated circuits, being aware of what the applications were and what the family of devices should be. One point I really want to add is that in spite of looking back and seeing their significance, integrated circuits weren't enthusiastically embraced by the customer base in the beginning. There were a lot of reasons. First of all, our interface with the customer is generally the circuit designer. Go in and say, hey, you don't have to do any more, we've done your design for you. It was not a pitch that went over especially well. I remember one aerospace company said we went in with our flip-flop. They had 16 different flip-flops with 16 engineers working on them. There was no way they could use one for anything. The QA folks had problems. They were used to taking transistors and measuring their current gain and their breakdown voltages and how these varied with time. Here they couldn't get a hold of the devices. They couldn't tell if the resistors changed. They couldn't tell if the transistors were changing. All they could do was see if the device worked. And besides that, the components in the integrated circuits were relatively poor. And the resistors were plus or minus 20% on a good day. They had high temperature coefficients. Circuit designers were used to using 1% resistors. Even the transistors were limited in their performance because bringing the contacts out to the top of the surface put some extra parasitic resistances in there that decreased performance. And beyond that, as Leslie pointed out, they were expensive. It cost more to buy an integrated circuit than it did to buy the components to build a circuit. This is where Noyce had his next brilliant idea, with selling integrated circuits for less than the cost of the components to build it. Of course, it was significantly less than our cost of building them also. But he started what has become a general reaction in the semiconductor business. The solution to all problems is cutting the price. A technology that really has endured. The rest, I guess, is history.
Thank you very much, Gordon. Our final speaker tonight is Jay Last. Jay earned his PhD in solid-state physics from MIT and was recruited by William Shockley to join the staff of Shockley Semiconductor Labs. He later co-founded Fairchild and then, with Jean Hoerni, established the Melco division of Teledyne. Before retiring from Teledyne, Dr. Last served as its vice president for technology. In late 1959 and throughout 1960, Dr. Last led the team within Fairchild R&D that fabricated the first planar integrated circuits, which were later brought to market as Fairchild Micrologic. Jay.
Okay, thanks. I'm really pleased to be here this evening, to be part of this discussion and see so many dear friends here. I'm really sorry that Bob Noyce and Jean Hoerni aren't here to participate in this event. It would really be great to hear all their discussions these discussions from their own perspective. It's hard for me to believe that 50 years have passed and it's equally hard for me to come to grips with what everything has taken place in this 50 years. The reality of today is beyond our wildest imagination in those days. We're living in a different world than the one that existed 50 years ago. The 1950s, the period we're talking about, were a golden time in technology. This was about a decade after the end of World War II, and all sorts of new technology were being worked on. This golden period was all based on the work of the previous 3 decades. In the 1920s, quantum mechanics was developed, providing the basic theory that would later be important to explain the operation of solid-state devices such as the transistor. The 1930s were a rather stagnant period due to the Depression. There was relatively little technological advance. Anything that cost a lot of money was just put on the shelf. The 1940s, the demands of the war led to technological advances of all sorts. New magnetic and electronic devices, radar, the first electronic computers. Also, the concept was developed of people working together in groups to solve complicated technical problems. So after the war, there was all sorts of unexploited technology coming from the previous decades. The technology buckets were really full, ready for use in all sorts of innovations and inventions. The transistor being a key one in this regard. The transistor was invented in 1947, and by the late 1950s, germanium transistors were in widespread use. Some work was taking place with silicon, primarily at Bell Labs, and a number of very important key innovations were being made in this period in the early 50s up to the end of the 50s. Silicon proved to be a lot harder to work with than germanium. It was interesting because it would operate at higher temperatures, and then an insulating oxide could be grown on the surface of the device. Bob Noyce had worked with germanium at Philco, and he told me how lucky we all were as a group never to have worked with germanium. The germanium was so easy to work with, but we didn't know that we were doing such a difficult thing with silicon. There was very little appreciation at the time of the enormous potential and versatility of silicon. Other semiconductors and device schemes have tried to compete with silicon, but have fallen by the wayside, except for special applications in general. In the late 1950s, with the Cold War concerns, there was a military need for small size and weight for airborne systems with high reliability. As has been discussed this week, there were many programs ranging from microassembly to molecular electronics. Most of the research programs were supported by the military. Fairchild took a different tack. We did not take government money for development. We wanted to keep our freedom to build the devices we thought had the greatest promise and to make our money by selling the devices. By 1959, Fairchild had a thriving business in transistors and diodes. All the company efforts, of course, were being spent to expand the product line and to update it using the new planar technology. A possible next step was the integrated circuit, but had a very low priority due to the effort that was being needed for all the other products we had. At this time, a lot of people and a lot of organizations were thinking of the form that an integrated circuit might take. Looking back on this has made me think a lot in the past few years about the nature of what inventions really are. Nearly all inventions are extensions of some existing product or technology. Very few are completely new ideas out of the blue. In the field of electronics, we can go way back to the invention of the telephone to see this phenomenon at work. Rudimentary telephone devices have been made for years by a number of people before Alexander Graham Bell filed his telephone patent in 1876. That very same day, Elisha Gray filed an almost identical patent. This led to vast amounts of patent litigation that went on for 30 years. In retrospect, Bell's main contribution was not in making the improvements that led to his first telephone, but in developing the complex interconnection system that make the telephone a practical device. We have so many examples throughout the years of the key developments such as this being worked on by many people at the same time, very often without the knowledge of the work of others. The successful inventor is in most cases one who is well aware of the state of the existing technology, sees that this technology can lead to a product that there will be a demand for, and he identifies the extensions of the technology that are needed to fill in the missing pieces to make the invention. He develops these missing pieces and then actively promotes the device. This is certainly the case of the integrated circuit. All these things happen that way. The basic concept was fairly easy to grasp. The problem was in expanding the existing transistor technology to make it. Jean Hoerni's planar process was the key to implementation. Also, a key Fairchild innovation was that we were making devices by batch processing with hundreds of devices on a silicon wafer. In one sense, you can say we did in Silicon Valley what Henry Ford did in Detroit using mass production techniques. So we already had this basic framework for the integrated circuit. The planar device with its silicon oxide layer provided a way to interconnect them on a wafer. Bob Noyce had the intuition and the foresight to document a feasible process to accomplish this. As we discussed already, he did this in January of '59, motivated to write down his ideas a week after he and John discussed the planar process. Work didn't start on the integrated circuit at that time. We didn't do much until the summer of '59, about 6 months after Bob had written down these basic ideas. The impetus really was the reports we were hearing of Texas Instruments' work in this area. And we were concerned that TI, who was developing a reputation for aggressively filing patents and enforcing them, would block us from some work efforts in this area sometime in the future. As a start, and in Bob Noyce's suggestion, I made a jury rig oscillator that we displayed at WestCon that August to show that we were really in the integrated circuit game. This consisted of a couple of transistors mounted on a plate and wired up, put in a package with some carbon resistors drawn with a pencil, a low technology product we call the Ticonderoga process. About the 1st of September of '59, work started in building an actual integrated circuit. I began to assemble a group to build this circuit. By early 1960, there were about 8 people involved in this activity. The first problem that we had to deal with was the conventional wisdom that we would never be able to make a working device due to what Jack Morton at Bell Labs called the tyranny of numbers. As arrays got larger and larger, they would inevitably contain some defective components, and an array wouldn't work. At Fairchild this time, our device yields on the new planar processor were just terrible. And when you started multiplying device yields in a potential circuit, we got 0 circuit yield very fast. When we started to look, though, at what device yields really meant, Izzy Haas went to the production line and started scooping up reject transistors at random and tried to build circuits with them. And we had a encouragingly high success rate. The reason was that we were using a device for a specific purpose rather than a general purpose device, and many devices that were scrapped for other reasons would meet our downgraded specifications. Also, defects turned out to be random on a wafer. There were areas of high yield and those of low yield. So there was a fair chance that groups of devices close together on a wafer might be good. The other problem we had to deal with was a concern that nobody would want our circuits. The simple circuits we could build might be considered nothing but cute toys. Any use would be confined to very specialized uses, where very small size was the overriding concern. Our customers for the discrete devices, as Gordon said, were the circuit designers, who were not inclined to turn over the circuit design function to the device manufacturer. They did not want to use our simplified circuits to build systems, but preferred to use their own highly optimized circuits. This was a problem that would continue for years. Bob Noyce in the Device Application Group, a true believer in the future of integrated circuits, started his missionary work, gave a number of papers in 1960 showing the enormous advantages of integrated circuits with potential low cost and systems compactness. In many cases discussing technological advances that we didn't have a clue how to implement. As far as building the first circuit has been discussed, there were three key ingredients: putting multiple devices on the same piece of silicon, interconnecting the devices, and isolating the devices one from the other. Our batch processing solved the first problem. We already had device arrays on a wafer and could add resistors and other needed components. Interconnections on the top of the silicon oxide using planar process had a high promise for device interconnection. The big problem we faced was isolating the devices. One scheme would be to do a triple diffusion, just diffuse a NPN transistor collectors and bases and emitters in a p-type structure. This was way beyond our technology at the time. We never seriously considered this. The most straightforward alternative would be able to diffuse a p-type web to the wafer and make a device in n-type islands. Slide one. Now, Gordon, you can. This is the time this slide really shouldn't come up. So you can see if we were starting with you could diffuse halfway through the wafer here. The blue area here would be the base, the basic substrate, and the blue sticking up would be the isolation. So we could make a transistor this way, interconnect them with keeping the planar oxide on the surface, the green part, and then metallization with the yellow. The problem with this was that boron was the only good candidate for the p-type diffusant. To diffuse halfway through the wafer here would require a diffusion time of about 18 hours. Boron was a very bad actor, and the diffusion times of as little as 15 minutes would start to soften the diffusion tubes and pit the silicon oxide. So this scheme we couldn't work with. So we decided to make the first integrated circuit by isolating the devices physically. This is shown in slide 2. This was really a brute force approach. We first made the array of diffused devices, the little red and blue structures. We then mounted the device upside down on a glass plate and etched the whole way through the wafer till we got to the green oxide. The device at that point was just supported by the oxide structure. Then we would fill this in from the back with an inert material that was compatible with silicon. This would have been a production nightmare, but at least prove that planar devices could be interconnected in an integrated circuit, and that circuits could be made by a batch process. By December, we were ready to make the first device. A sketch by Lionel Kattner is shown in slide 3. The device here was about 30 thousandths of an inch on side. It was roughly the size of the first transistor we had made 3 years earlier. All the logic needed for a computer could be built up using about a half a dozen different circuits of this sort using DCTL. The biggest circuit having about 6 transistors. We set to work and made a successful device in May 1960, a date that at least a few of us would like to commemorate. The circuit was encapsulated in a small TO18 can with 6 leads. A picture of this circuit, as we've seen earlier tonight, and it was shown in Life magazine in March 1960. You can see the small transistor can. It had 6 leads on it. The circuit was about the size of the D and the dime, as was pointed out in the advertising for the device. Someone looking at this circuit said to me that we were going at the problem all wrong. Life would have been so much simpler if we'd worked instead of trying to make bigger dimes. This can was only about a quarter of an inch in diameter, and it proves very difficult to use. So we backed off and started to put the devices in a larger can, about twice as big. It was much easier to use. This TO5 can was used for several years until the dual inline packaging came along. We were making these circuits at low yield with a lot of problems due to the diffusion control and the photoresist. We had a lot of shorts due to holes in the oxide. But we managed to make hundreds of working devices using this physical isolation technique. One of our main efforts, of course, being a continued search to find a material that would be a good isolating thing. We investigated dozens of compounds. We worked on a design of transistors that would be optimum for the circuit. The one problem that we had to line up the array of diffuse devices on the top of the circuit with the isolating web that we were going to diffuse the whole way through the circuit. We couldn't do this mechanically, but we realized that silicon is transparent in the near infrared. So we had built a complicated infrared alignment device showing the brute force steps that we were going through at the time. This circuit was still an impractical, brute force, low reliability, low yield device. We had demonstrated we can make circuit arrays by mass production techniques. Interconnect them over the oxide using extensions of transistor fabrication techniques. We began to deal with a lot of actual and philosophical problems relating to treating transistor arrays as circuits rather than devices. This device application group worked on these problems, how to specify and test a device as a circuit rather than treating it as individual transistor, testing individual transistor parameters. The key development that made the integrated circuit practical occurred in late 1960. Improvements in boron diffusion were taking place steadily at Fairchild, both in R&D and in the production engineering groups. Production engineering began to use a methyl borate compound as a boron source, which proved to be a marked improvement in keeping the diffusion tubes from being destroyed and the boron pitting the silicon oxide. Against all the conventional wisdom at the time, Izzy Haas and Lionel Kattner thought it was worth a try to do the long-term diffusion using this new boron diffusion technology to make the device shown on the first slide. I'll put that back on again. So they were taking an N-type material, diffusing halfway through the wafer from the bottom with a P-type diffusing the web down from the top until they met. In order to keep this down, we worked with the thinnest crystal as possible, 3 mils, which was extremely fragile. And one of our big problems all the way through was breakage. We made the oxide as thick as possible to provide some mechanical strength. And we found, Izzy and Lionel found that the diffusion apparatus would really hold up for this 18-hour diffusion. A working device, a truly diffused integrated circuit, was produced in November 1960, a year after we started the integrated circuit program, a little less than 2 years after Noyce wrote down his ideas for the integrated circuit, and Jean Hoerni made the first planar. It was 3 years after we went into business, and 5 years after we started to work for Shockley. As was discussed the other evening, the fact that we made the circuit really startled a lot of our competitors. In line with the idea that the time for the integrated circuit was right and a lot of people were thinking of it, as has been discussed, it's very interesting to see that the key inventions held by people in 3 different organizations with no knowledge of the work of the others. Kilby getting his patent for the multiple devices, Noyce getting the interconnection patent, and Lehovic getting the electrical isolation patent. In the first half of 1961, the diffused integrated circuit quickly became a production device. The family was filled out with the introduction of a flip-flop, a gate, half-shift register, a buffer, half adder, and a counter circuit. The largest circuit having 8 transistors. By December of 1961, about 5,000 production devices had been built, and the sales were about $500,000. The circuits were selling for about $100 a piece. As has been discussed, the integrated circuit certainly didn't take the world by storm. It was looked on as a high-cost device for special military and space programs where small size and weight were worth paying for. Most orders were sample orders, with few turning into production orders in the first years. The use of epitaxy, where we could put a thin conducting layer on the top, negated the need for these long boron diffusions to make the substrate. Work on this started in Fairchild in 1961. In the next few years, more flexible logic circuits such as DTL took over from the DCTL. Linear circuits such as operational amplifiers lent themselves to integrated circuit techniques. Here, matched components rather than absolute values were important in general. This was a personal interest of mine, and at Teledyne, where Jean and I were working at the time, we made some very interesting linear circuits for specific military and space programs. Technology steadily improved in the next few years. Many companies went into business and sharing a very small total pie. In 1964, Gordon realized that integrated circuits had reached the point where they could be sold on the basis of their cost, and Moore's law would prevail. Integrated circuits then began to be used for a wide variety of non-military applications in a rapidly accelerating manner. The big advance leading to the integrated circuit today was the use of MOS technology to make smaller and smaller devices in larger and larger arrays, reaching a point now where millions of devices occupy the area where we originally just had a few dozen devices. This didn't happen by accident. It involved a tremendous development activity. Most silicon fabrication companies put at least 20% of their sales into R&D, and this process has continued for 50 years. So hundreds of billions of dollars have been spent to improve this technology to the point we are today. Gordon, who always has an interesting way of describing things like this, may have some interesting way to point out what this really means. So today we live in a world where integrated circuit chips play a basic role in our daily lives and the way we communicate with each other. But through all of this, silicon still reigns supreme, having steadily fended off all competition from other materials and fabrication technologies. What will the next 50 years bring? My crystal ball is still as cloudy as it was 50 years ago, but some directions can be seen. The last century can be looked on as the century of physics. The century we're in now will prove, I think, to be the century of biology. Interconnections of electronics with human biological processes will expand, as will all sorts of new products that we cannot yet imagine, which will require arrays of devices at very low prices. It's been a very great ride for me these last 50 years.
Well, thank you very much, Jay. It seems that we now have about 15 minutes or so to ask you to answer some questions. And the first two questions from the audience both connect to Shockley. So maybe they're organized chronologically, who knows? But the first question reads, how did Shockley feel about you all leaving? Or maybe rather than speculating on his feelings, it could be how did he react? So I guess that's for Gordon and Jay.
Well, I had the privilege, I guess, of telling Shockley the group was leaving. And he started to go through the staff one at a time to see who were members of this traitorous group, as we got designated later. And I was about third on his list and the first one of the group that was leaving. So I told him there wasn't much use going through the rest of the staff because most of them were involved. and Shockley kind of hung his head and walked out the door. He didn't take it with great enthusiasm.
Jay, did you have anything to?
No, I just go along with that. It was
Okay. Fair enough. Shockley question number 2 reads, Shockley was not a good manager, but obviously a genius at the selection of sharp people. How do you think he did this? Anybody have any ideas?
Well, he was very extremely bright scientist. He could look at what other people were doing and very quickly do that, and he could look and see that we were probably going to be a pretty creative group. So he was hiring us, and he was looking to see what skills we had that would be complementary to the rest of the group, so we could fill out the whole group with the group of us. The group of us that left, the 8 of us.
Ezra Turner, he was very charismatic. Clearly, he knew the business he was looking at, and he was very successful in recruiting the people he went after. The one thing that was a surprise that probably we should have been more aware of was that none of his group from Bell Labs has joined him.
One of the things that I learned about when I was researching this was that William Shockley required a psychological evaluation of you guys, had you take these tests with sort of Rorschach ink dots and such, which wasn't as uncommon as you would think. But it seemed that he tested everyone for compatibility with each other and failed to test them for compatibility with William Shockley.
Another interesting aspect to it, that Shockley had a very unusual way of identifying people. And what he would do, he would get the list of people who had done jobs at a place like the Bell Labs or the Lawrence Berkeley Lab, right? And he, rightfully so, he thought that these people would be the right ones to choose.
And a different tack entirely, I think this is a very interesting question, which is, how did you all being the Fairchild Semiconductor co-founders, settle your differences, presumably in the period before you hired your own boss?
How did we what?
Settle differences or coordinate your activity, I think.
We did coordination by having weekly meetings where we straightened this stuff out, and I don't recall very many serious
difficulties we had. We were each we were all doing our own part of the job. We were depending on everybody else to do their part, and worked out. We just had a great respect for the people that were doing a part of the job that we wouldn't have personally been able to do ourselves. So we didn't fight over this stuff.
All right. The next question reads, how much time after the invention of the planar transistor passed before it became obvious to everyone, or perhaps clear to everyone, that that was the best way to make transistors?
About 10 minutes.
For everyone in the company, clearly a planar transistor was a better transistor. There, however, was a very serious yield problem with the early planar transistors. It made them significantly more expensive to make than the mesas. And until we got that solved, it was not completely obvious.
When would you say, in terms of customers, it became clear that it was going to be a runaway success?
Well, the device parameters were so much superior to what we were with other devices that it just caught everybody's attention immediately.
I think this question was largely addressed about how you convinced customers, especially the military, of the reliability of the early integrated circuits to the extent that they were reliable.
We did the standard life testing procedures, put them at elevated temperatures, lower them down again, do life testing by taking hundreds of devices and running them at high, under severe conditions. This is the same thing that we've done for any of our other products.
I think maybe I'll take the moderator's prerogative and ask you a question of my own, which was, and I'm sorry, it's for Gordon and Jay primarily, but it's the question of how do you know that you're in the middle of sort of the next big thing technologically? It seems like that you were both involved in a number of these moments where you were involved in fundamental developments in technology. And I was curious if there's something that signals to you while you're in it that that's what you're in, or not.
Now, you look back from 50 years. At the time, we had no appreciation of the magnitude of the possibilities that come out of integrated circuits. You know, it was a nice addition to our product line, but it wasn't clear it was going to be completely revolutionary, at least not clear to me.
And the other thing is, these things were really hard to make at low yield, and we were always focusing on, can we make the thing, not how is it going to change the world.
Let's see. This is a question specifically for you, Gordon. It reads, Moore's law is, of course, part of the vernacular and folklore of Silicon Valley. In your opinion, to what extent is it a natural law, and to what extent a goal and a tacit marching order for engineers?
Well, it's obviously as fundamental as Newton's law. There was an observation that somebody hung the name on. Recently, it has become a benchmark that the industry drives to. It's a funny technology. The next step in the technology makes everything better. Things get higher performance, can use lower power, you can increase system reliability, and they get cheaper. So people recognize they have to stay at least on that curve, or they become technologically behind. So with the SIA and other organizations putting out all these projections that are similar to Moore's law, people know where they have to be competitive.
Next question, perhaps best addressed to the entire panel, asks, can we reinvent Silicon Valley again to create an exciting environment like the 1960s? Anybody care to address that? If not, we can move on. Sorry to whoever wrote that. This question reads, how can we record and organize and recognize the many chemists, programmers, instrument makers, office managers, and others who made these products possible? Leslie or Christoph, any thoughts in that direction?
Well, I mean, it sounds like the Computer History Museum is already trying to take some steps in this direction with this fairly, actually quite, I should say, extensive oral history process that's going on. We at Stanford have our own Silicon Valley collections where we very much love for people's old notebooks and any sort of lab books they kept, any sorts of old papers, these sorts of things, and we consider it our responsibility to keep those and preserve them and make them accessible to other people. So I do think it is an ongoing effort, and it's a very difficult thing to do in a place like Silicon Valley where everyone is always looking forward. And so taking time like this to really recognize the value of the past and where these things came from is very important.
Another problem is that the world loves a hero, and the people discussing this and writing about it tend to pick one person and attach the whole process to them. So we have to do as much as we can whenever we're discussing these things, to discuss the contributions of everybody involved.
That's right. It's all kind of a continuum with a whole bunch of little steps, and one of the steps gets all the credit for what has happened, really, and that's kind of the nature of history, I think.
And it really speaks to the value of documentation. I mean, Jay and I were talking about this before. Part of the reason we're able to have as a discussion as we're having up here tonight is that Jay was a pack rat. Excuse me, a pack rat. He kept so much, and that enables us to actually not rely simply on people's memory and not simply to think about the most charismatic guy in the room, but to sit down there and look at the hard work that all of these people were doing and when they were doing it and how they were talking to each other.
Christoph, this question is specifically for you, and I'll just paraphrase it, but it asks you to talk a little bit about the sort of history of manufacturing on the peninsula that provided essentially a resource for the semiconductor industry.
So, as you know, the semiconductor industry was not the first industry in Silicon Valley. Many industries preceded the semiconductor industry, especially the vacuum tube industry, and also the scientific instrumentation industry. And these industries provided important skills that were later used in the making of semiconductors. And I remember speaking once with Julie Blank, who told me that when he was at Fairchild, he was actually working very closely with machine shops that had been working before for the tube industry, and also the people making instruments, and also the people making slack, right? So these were important skills. They were also the glass making skills that also came from the tube industry. So there was really a basis, if you will, that enabled this industry to grow here in Silicon Valley.
Oh, thanks. The last question that I'll pose is, what advice might you give to young engineers? And I think that's probably for Gordon and Jay in particular. Advice to young engineers. Any thoughts on that?
What they ought to go into now?
Yeah.
I don't know. I don't know what the next big thing is going to be. You know, things keep coming out of the woodwork. I wouldn't have predicted a Google or anything like that a few years ago. These are new ideas that people generate. If you can climb on one of those, you've got a chance of having your own 50th year reunion in a few decades.
Well, one thing I would say advice would be get as broad an education as possible, because you don't know in what area these new devices are going, what inventions are going to take place. And the broader your background, the more likely you are to understand these things.
Well, I'm afraid that's all the time we have for questions, and I'd like to turn things over now to John Holler.
Thank you very, very much, all of you on the panel. It's just been a fantastic evening, and I wonder if you would join me in giving a round of applause to David Brock, who produced all of this, and it's just been so wonderful. David, thank you.
Thank you.